Hello everyone, welcome back. So we've been talking about differentiation, and today we will talk about Richardson extrapolation, which is one of the most elegant tricks to calculate numerical differentiation. And by the end of this video, you will understand that, the power of this idea, right? So when we derive the formulas for forward and backward difference, if you remember that we used the Lagrange polynomial interpolation, right? And then we found out the formula there and calculated the error. So there is a different trick that will be used now, and you will see that this is way more elegant, and you can go up to any order of accuracy you want, but it will take some computational complexity, but still this is something really elegant and can be applied in calculating differentiation, right? So if you remember correctly, that the formula for the central difference was written something like this: f of x plus h, okay, let's call this x1, f of x1 plus h minus f of x1 minus h by twice h. Okay, and you can calculate different values of h. The smaller the value of h, the better for truncation error, but we learned in the last video that we cannot take it to be arbitrarily small, because then you'll have some rounding error creeping up as well. So let's give it a name. This quantity is the derivative of f at point x1, and let's give it a name. We call it dh. This is the defined symbol, so dh is defined like this. All right, so now if you remember Taylor series, then we can write f of x1 plus h equal to f of x1 plus f prime of x1 into h plus f double prime of x1 by 2 factorial h square plus, okay, let's not give prime. I think it's better to write with 1s and 2s. So this 1 means the first derivative, this 2 means the second derivative. Okay, so f3 of x1 by 3 factorial. I'll write up to 5 terms because you'll see why it is important. H cube plus f4 x1 by 4 factorial plus into h to the power 4 plus f5 of x1 divided by 5 factorial into h to the power 5 plus order h6. Okay, so I wrote up to 6 terms because you will see that this is important. Similarly, I can calculate f of x1 minus h. Now what will be the formula for that? It's really easy to understand. Just replace all the h's here with minus h. Okay, and if you replace that, you will see that whenever you have an even power of h, that means h square or h to the power 4, it will not change. It will not change the sign. But whenever you have an odd power, that means 1 or 3, here it's a 1 or 3 or a 5, you'll have a change in sign. All right, so you can easily see that this will be f of x1 plus minus f1 of x1 h plus f2 of x1 by 2 factorial h square. There's no change of sign because it's a even power. Then you have a minus f3 of x1 by 3 factorial h cube. Similarly, plus f to the power f4 x1 by 4 factorial h to the power 4, and you have a minus sign f5 by 5 factorial, and you have a h to the power 5, and you have plus order h6. All right, So now if I want to calculate dH, which I defined here, so I have to subtract, defined here, so I have to subtract these two series, right? And if you subtract, and you have a 1 by twice h already, which is divided, so let's keep it outside, 1 by twice h, and whatever you have in the series you have to subtract, and you will see that you can check it by yourself that all the even powers will go away, because whenever you have a same sign and you take the minus in between them, they will cancel, right? So what you will be left with is, whenever you have an opposite sign and you put a minus, you get the same sign, so it will be added. So you'll get 2 f prime of x1 plus 2 f triple prime. I should not use prime because I was using 1 there. So let's use f1, 2 f3 of x1 by 3 factorial h cube plus you have a 2 times f5 by 5 factorial f5 at x1, okay, into h to the power 5 plus order h7, because the term with h6 will get cancelled. All right, it will get cancelled because it will, the even powers are getting cancelled. So now you can take this common factor 2 outside and cancel with this 2, okay? And what you can also do is that you can divide by this factor h. Oh, I missed a h here, sorry, I missed a h here. Here I missed this because I had this f1 times h. All right, so I missed that, sorry for that. All right, so if you write it down, and what you do now is you multiply by, you pull this bracket off, so you multiply by 1 by 2h to each term, then what you'll be left with is nothing but f1 at x1 plus f3 of x1 by 3 factorial h square, okay, plus f5 x1 by 5 factorial h to the power 4 plus order h6 again, because you're dividing by h, so the power will be reduced by 1. All right, so now you can see that this is the exact value of the derivative which we can calculate from, not the exact value, but this is the this is the exact value of f of x, and whatever you have left here as rest, these all of these terms are the error terms, right? So if you use this formula here, if you use this formula for central difference, then you'll get the exact value plus an error of order h square at most, right? There are higher powers of h, but the most dominant one for h less than 1 is h square. So it's like the central difference. It is the central difference, and we proved it in a different way, that your your error is of order h square, right? But can we make it better? That's the question. Yes, we can. How we can do that? We showed that this formula dH is equal to f prime of x1 plus f, okay, I'm using primes again, f1 of x1 plus f3 of x1 h square by 6, which is 3 factorial, plus f5 x1 by okay, let's keep it factorials, I think that's better. So keep it as 3 factorial, this is as 5 factorial h to the power 4 plus order h6. Okay, but if you look at it closely, our h is our choice. We can make it to be 0.1, we can make it to be 0.01, or we can make it to be whatever we want, right? It's our choice. So what we can do, as I can calculate dh because I'm doing a numerical differentiation, so I can obviously have these values of functions here and I can calculate dh, right? But I can similarly calculate dh by 2. Okay, then what will it be? This is nothing but f1 of x1 again, but now f3 of x1 by 3 factorial, and you will have h by 2 whole square, plus you will have f5 of x1 by 5 factorial, and you have h by 2 to the power 4, plus order h6. Order h6 will not change because h and h by 2 has the same order. Okay, so what I want to do now, I can calculate dh, I can calculate dh by 2, that's fine, but what I want to do is to take their combination in such a way that the order h squared term goes away. Okay, let's see how to do that. So if I want to take a combination such that this combination goes away, then what do we have to do? We have to multiply this term by this factor and then subtract, right? So let's see. So what I want to do is that I want to calculate, so you'll have this 2 square times dh by 2 minus dh. Okay, then what will you get there? You will have this f1 multiplied by 2 square, which is 4. So let's write it, 2 square f1 of x1, and from dh you'll get f1 again, so 2 square minus f1 of x1. Okay, but the second term is cancelled because this is how we chose the coefficient 2 square, right? So these green boxes will go away. All right, then what you get here is plus f5 x1 by 5 factorial. You'll have h to the power 4 here, and what you'll be left with is 1 by 2 to the power 4 into, I wrote the this term from here. Okay, so you'll have 1 by 2 to the power 4 into 2 square, right? And similarly you'll have minus f5 x1 by 5 factorial h to the power 4. Okay, and plus you'll have a order h6 term. So let's see how to simplify this. So you can see that I can write 2 square dh by 2 minus dh, which is equal to 2 square minus 1. I take a common factor and write f prime x1. Alright, and what you'll be left with for the second term is plus 1 by 2, 2 square divided by 2 to the power 4 will give you 1 by 2 square, which is 1 by 4. Okay, let's write it as 1 by 2 square. 1 by 2 square minus 1 into f to the power 5, f5 x1 by 5 factorial h to the power 4. Okay, plus order h6. So what I'm trying to do here, I had a formula for a derivative which gave me an error of order h square. Now I have taken a combination in such a way that order h square term has gone away, right? So what I'm left with is 2 square minus 1 by times f prime. So did I get the derivative? No, because I have to divide by this number. If I divide by this number, then I'll get the value of the derivative. All right. So if you divide by 2 square minus 1, then you see that 2 square d h by 2 minus dh divided by 2 square minus 1 will give you f prime of x1, right? And you'll have this plus 1 by 2 square minus 1 divided by 2 square minus 1. You can simplify this by yourself. This is just some numerical manipulation which I don't really matter to me right now for this purpose. 5 factorial. This will be a sum number, and you'll have f5 x1 into h to the power 4 plus order h6. So what is the thing to notice here? The most important thing to notice here is that from this combination, I can calculate this combination, because I can calculate dh, which is just f of x plus h minus f of x minus h by 2h. I can calculate that numerically. But I can also calculate dh by 2. Then I can obviously take this combination. But if I take this combination, the gain is my error is of order h to the power 4. Alright? So this is the most important punchline for this, that you can make your error less by doing one more step. Can you make it better? Obviously you can make it better, because let's define this red box as dh1. Okay, so now you can take again dh by 2 1, and then you can calculate again. You can take a combination in such a way that this h to the power 4 term goes away, and whatever is left will have an error of order h6. Okay, so first you choose this multiplicative factor 2 square in such a way that you want to cancel this term, and then you get some coefficient before f prime. Here f prime, you have a 2 square minus 1, so you divide by that here, and then you get it. Alright, and which makes sure that my error is of order h to the power 4, which was h square before. Okay, so I have one more comment to make here, and then I'll finish. So if I have like arbitrary orders, for example dh f prime of x plus chn, and I don't even need to know what c is. Sorry, because if I have this dh of order h to the power n, whatever coefficient here is f double prime, triple prime, or to be precise it would be fn or whatever it is, I don't care about that. So so the punchline is, now what can I do? I can take dh by 2 again, and I'll get f prime of x1, and I'll get c h by 2 to the power n plus order hn plus 1. Okay, now what will be the combination? Now you can easily see that the combination will be, you have to cancel these two terms, right? So if you want to cancel these two terms, your dh1 will be, you have to multiply this by 2 to the power n, correct? So this is the point to understand, that you'll have 2 to the power n in minus 2 to the power n into to the power n into dh by 2 minus dh. Then what will be the coefficient for f prime? You will divide it by 2 to the multiply it by 2 to the power n and take a minus 1. So you have to divide by 2 to the power n minus 1. So this is very easy to calculate, and then you will see that your order h to the power n error will go away. All right. So another thing to notice here is that h by 2 is just taken for convenience. You could have used dh and d2h. That would also be fine. Or you could use 3h, whatever you want, whatever you prefer, it's fine. As long as you calculate it correctly and you can isolate this f prime, you'll be good to go. All right. So this is an amazing idea. If you do it like for 3-4 steps, you can get, I mean, like of 3 or 4 orders better in your computer. All right. So this idea, this was I mean, an outstanding idea by Richardson. He was an undergrad when he actually invented this way of calculating numerical derivative, and in the 19th century, he actually predicted the weather of a city by this formula. But he estimated that he would need 60,000 people to estimate the weather for the next day. But obviously they didn't have computer back then. But now, using these formulas, you can actually calculate the weather. All right, you don't need 60,000 people. You just need one computer. All right, so this is the power of numerical methods, and I hope you enjoyed. This is the end of differentiation. And if you still have any questions, please don't hesitate to ask me. Thank you so much.